Hi, everybody. Welcome back to Mount Moleville. Ready to start learning about some blue square stoichiometry problems? Now, granted, I might have gone a little fast in the green circle problem video. I might seem to be going a little fast sometimes as I go through some of these problems in the blue square as well. But I'll always give you a lot of links for you to go practice elsewhere, like other mountains, to practice your stoichiometry problems on. So please feel free to go to those or come back and ask any of us any questions you have about these problems. So let's take a look at Mount Moleville's blue square problems. Now, before we get there, I'd like you to notice on the bottom, you might need to know how to get to, Graham Lounge or Mole Shop or the Atoms and Molecules House. So to get around on Mount Moleville, to go from grams to moles, you're always going to need something like molar mass way to travel on. So these are nice little things to remember. And anytime you want to go from mole shop to atoms molecule house, then you are going to need to maybe put on your goggles and go out into Mount Moleville and walk on Avogadro's Road. Woohoo, Avogadro's Road. So keep that in mind as you're traveling around in stoichiometry Mount Moleville place. All right. Last but not least, in this video today, we are going to emphasize something way up at the top of Mount Moleville known as Empirical Formula Camp. Yeah, those are cool little buildings. Let's see if we can get there. Okay, let's play. So to start our playing in this blue square region, we're gonna try to balance and see what these reactions are all about. And here's the first one I want to show you. You might be asking, hey Nick, why should we care about this reaction? Well, this is ethanol combusting in oxygen, and usually that's not very exciting until you see this. Yep, that's really cool. That is a gaseous ethanol reacting with gaseous oxygen in the air to produce a very beautiful blue flame out of those jugs. Who knows? We probably won't be doing that one in lab this term. Sorry. Okay, but I thought I'd show you sometimes these chemical reactions are really important. They help us understand what will catch on fire and what might not catch on fire. Okay, so let's play around. The first thing we're always going to want to do with a chemical reaction is balance it. So when you go to balance your chemical reactions, please make sure to try to start balancing the atom that appears in the fewest number of molecules or substances. So in this overall reaction, we see that there are four different substances. Okay, so four of them, 1, 2, 3, 4. Right, so now look at how many times, say, carbon shows up, how many times hydrogen shows up, and how many times oxygen shows up in those four different substances. So I spy that carbon really only showed up in 2 out of the 4, hydrogen only shows up in 2 out of the 4. So you could start with either one of those, but do not start with oxygen. It shows up in all 4 of those up there. So let's start with carbon. It's right at the beginning. I see 2 carbons in ethanol. And on the product side, I only see 1 carbon in carbon dioxide. So I'm just going to place a 2 in front of the CO2. And I like to place a 1 in front of the C2H6O. Some people don't mind if you leave that blank. But the reason I like to place the 1 there is it reminds me, don't mess around with that area. Do not try to add a number there later on, for example, to balance some other atom. It's already got a coefficient in front of it. Leave it be. So now we got the carbons balanced. Hydrogen would be next. So I look at ethanol. I see 6 hydrogens in the ethanol. I look in the product side. There's only 2 atoms of hydrogen in the water. So I'll need 3 water molecules to create 6 hydrogen atoms total. Mass must be conserved. So last but not least, I only have one molecule left to put something into. That's the O2. So hopefully I'll have more oxygens on the product side so I can add a little or at least equal the number of oxygens on the reactant side. So going through, you see there's 2 CO2s, so that's 4 oxygens there, and 3 H2Os, 3 more there, so you have 7 oxygens on the product side over there. So I need 7 oxygens on the reactant side. Don't forget ethanol has 1, so the O2 has to give me 6 more oxygens, which is beautiful because then all I need is a 3 in front of it. And now this equation is fully balanced. It tells me that every 1 mole of ethanol will react with 3 moles of gaseous oxygen to produce 2 moles of carbon dioxide and 3 moles of H2O. And now I can create my fire in a jug and never waste or use too much ethanol to the oxygen and know exactly how much product I'm going to make. Okay? Let's play. What if I gave you 0.045 grams of ethanol and you were trying to combust it like it was in that video? How many moles of carbon dioxide would come out of that jug with 0.045 grams of ethanol? This is where I'm going to pause for a second. Feel free to pause the video and then try this problem on your own. And then I'll show you how I do it. Okay, so pause. 4, 5, 4, 3, 2, 1. Okay, so this is how I would solve this problem. I'm going to approach stoichiometry problems using something known as dimensional analysis, otherwise known as unit analysis. This is a way that will allow me to make sure that my answer has the appropriate units for the question that's given. So in this problem, there are a couple ways you could do this. My favorite way to do this is to start with maybe even the number given in the problem, 0.045 grams of ethanol. And now your job, my job, our job is to cancel that grams of ethanol and convert it to moles of carbon dioxide. Everything has to be in front of me. I either have to use numbers that are in the problem, I either have to use molar mass or Avogadro's number. These are the only things available. That should make our life easier. So notice if I want to cancel grams of ethanol, the only thing I can use is grams of ethanol per mole of ethanol. So I went and grabbed its molar mass so that I can convert grams to moles of ethanol. But now the question is like ethanol to carbon dioxide. How do I make that conversion? How do I go from the ethanol to the carbon dioxide? So to do that, you need to look up there at the balanced equation and use the mole ratio we just got from balancing that equation. So that's what that ratio is. And these are all multiplications or divisions. This dimensional analysis works very well that way because then when I multiply these two numbers together, I can cancel out the moles of ethanol. And what I am remaining with in my final answer is moles of CO2. And so if I just multiply the top, the numerators, and divide by the bottoms, the denominators, I end up with my final answer of 1.95 times 10 to the minus third moles of CO2. And I should have some high degree of confidence in this because my units cancel to give me this number and represent the number that I want for my question. Please don't feel like writing out all of these ratios is a waste of your time. I know a lot of you might want to just plug away and put the numbers into your calculator and spit one out so you can get on to the next question like this one. But understand, for us to give you credit, we're the ones you're writing the answers for. Please show us how you do your work. And you got to show every little piece. So in case some little flip goes off, we got the error multiplied instead of divided. We can see that in your work and the whole problem doesn't explode on you. You just get a little teeny ding. Oh, flip that ratio. So life will be a lot better for you. Okay, let's try this one. What if we took the same mass, 0.045 grams of ethanol, and we wanted to know how many grams of oxygen were consumed or used so that you don't use too much air in the room, I guess. Who knows? These are fun little questions to try. So again, I want to try starting this one with the value of the unit that my final answer is. So here's another way to do unit analysis or dimensional analysis. Take a second to try it, but try using the very first ratio should have the unit that you want in your answer. Try this one. 5, 4, 3, 2, 1. All right, welcome back. This is how I did this problem. When I took the ratio, I'm trying to find grams of oxygen. Then the very first ratio I used down here, notice, is the molar mass of oxygen. That's the only place I'll ever get the grams of O2 for my final answer. That has to be grams of O2. And now the rest of my unit analysis problem is trying to cancel out, how can I cancel out moles of oxygen that came with my molar mass? So here I can go back to the balanced reaction. And I don't want to use Avogadro's number here because I'm not trying to find molecules of oxygen. So use what is available to you to help you start canceling units out. Moles of O2, moles of O2, beautiful. Now I have moles of ethanol because I had mass of ethanol given in the problem. So I can start canceling out moles of ethanol with the molar mass of ethanol to get to mass of ethanol, which can cancel out with the given value in the problem and end up with the same units that I was hoping for. Ding, 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 grams of O2. So this is another way you can do dimensional analysis, either starting with the value given in the problem, like the one above, over there, or, excuse me, over there, yeah, or the one where you start with the unit of the answer. That has to be somewhere in the problem, and then you try to cancel out all of the other ones until you have just the unit of your answer. Okay, so if you want more practice, here again are lots of websites that you can go to play with and practice doing this manipulation of playing around grams, moles, molecules, atoms, converting between all of those in a balanced reaction. This is definitely blue square stoichiometry. Okay? Let's play for you. You try this one. Do it any way you'd like. See if you come up with the same answer I do. All right. This is how I solve this problem. I need to remember to balance the equation because I can't play with it and use the mole ratios in converting copper sulfate to iron and iron to copper sulfate if I don't have a balanced equation. So please make sure you don't skip over that part and get all excited about saying, ooh, there's a molarity up there in the problem. I'm going to use molarity and I got grams, and start throwing all those numbers into your dimensional analysis without balancing the equation. So I started with iron because it only appears in 2 of the 4 molecules. And then I can put a 1 in front of that Fe2 iron sulfate in the product. That way I know I'm not going to mess with that one. And then I can start playing around with the copper or recognize that the sulfate is a species that is intact as a whole ion. And I have 3 of those in my product right up there. And I need 3 sulfates in my starting material. So my best advice is to make sure you throw 3 sulfates over here in the starting material, treating them as a single species. Now I know I need 3 coppers. Now you could have come across this balanced equation in other ways. This to me was the least painful. All right, now that we have it balanced, now we can play with doing it either way you want. I threw 1.45 grams of iron as my first ratio in the problem. And now my goal is to start canceling out grams of iron until I can get to milliliters of this concentrated solution of copper sulfate. And if molarity is an issue, you don't quite remember what it is, please go back and check out the green circle stoichiometry problem video. we play around with molarity in there for a nice review. When we do this, you can see all my units cancel. Grams, grams, mole ratio from the balanced equation, moles of copper sulfate from the molarity, moles per liter, and I highly recommend that if the answer is in milliliters, that you actually show this ratio conversion of 1,000 milliliters to 1 liter. In your head or on a calculator, I know you can do it, but in all honesty, I've seen students make so many mistakes on multiplying by 1,000 or dividing by 1,000. They knew there was 1,000 involved somewhere. Put it in your dimensional analysis. Let that do the work for you and you won't make any mistakes. It's really nice. So I would need 77.9 milliliters of this solution to completely react with all of the iron and use it all up. That's kind of cool. You put in less than 77.9, you're going to have excess iron in this reaction. It won't be able to be used up. So this is like a recipe. It tells you what you need to use up all of your reactants. All right. Tons more websites if you want to keep playing with this idea that incorporates molarities, balanced equations, and more blue square intermediate stoichiometry problems. All right. Lastly, in this video, I want to know how we can get up to empirical formula camp. How do we get there? Okay. So let's define empirical formula. It is the lowest whole number ratio of atoms in a molecule. Okay? It's not necessarily what the molecule has as its complete formula. That would be known as its molecular formula. So it's one step away from getting to the molecular formula. But it can be very helpful at times, especially if you're given information that only allows you to get an empirical formula. So playing around with something like we had ethanol earlier, let's start playing around with something like high fructose corn syrup. It's so bad for you. Don't ever eat products that have high fructose corn syrup. Please feel free to ask any of the instructors why it's so bad for you. When you, it's a cool story. But that aside, what if you were given this information about the fructose that is the main component of the high fructose corn syrup? Okay. What if you were told that this fructose was composed of 40% carbon, 53.3% oxygen, and 6.7% hydrogen by mass? Very important, by mass. And I gave you 100 grams of this fructose. Could you tell me, out of that 100 grams, how many grams are carbon, how many grams are hydrogen, and how many grams are oxygen? Take a second. Pause. All right. Start the video up and let's see if you get the same answer I do. So the beauty of using the 100 grams of fructose in my problem is that I can convert the percentages by mass directly to the gram values. As you can see, 40% carbon means that out of 100 grams, I'll have 40 grams of carbon, right? And so on, because all of these grams will sum up to the 100 grams that I gave you initially. Keep this in mind that there's a lot of these percent composition problems where they don't tell you how many grams of the substance you have, but just ask you, what's the empirical formula? The very first thing I would do is start with 100 grams of it to figure out its empirical formula and create this beautiful little gram ratio down here. Okay? Because these masses can get us to an empirical formula because I know I can change mass into moles. Right? So yes. Let's use these masses to get our empirical formula. Start by converting all these masses to moles, and what we'll do is we'll end up creating a mole ratio between carbon, hydrogen, and oxygen. So if we use the molar mass of carbon, oxygen, and hydrogen, we can convert all of these masses to moles. And if I were to pretend to write a formula now using these molar amounts combined to make fructose, the one molecule of fructose, I might be tempted to say, well, that formula is C 3.33 H 6.65 O 3.33. Yeah, done. Wait, there's only one problem. Whole number integers. I can't have 0.33 of an atom. So that doesn't work very well. So you're close though. These are all perfect mole ratios. Why don't we just divide by the lowest number in the formula to convert to a whole number integer? So I divide all of them by 3.33. And as you see, that math works out beautifully to give you an empirical formula for fructose of CH2O. Keep in mind, again, this might not be the molecular formula for fructose. It's just the lowest ratio of atoms in the formula of fructose. Okay, I think that's rather cool. Now, summary of this, start with your mass ratios, assuming a percent composition with 100 grams of whatever substance you're using. Take that mass ratio and turn it into a mole ratio, as you see above, and then convert that to the lowest whole number integer in the formula to help you create the empirical formula. And you've made it to empirical formula camp. Woohoo! Well, if you really want to know the molecular formula for fructose, it is some whole number integer higher than CH2O. Fructose is a sugar, which is known to have a formula of C6H12O6. Notice it's 6 times more than the empirical formula. And so we would have to give you information about that molecular formula, like that molecular formula's molar mass, for you to compare it to the molar mass of your empirical formula. You would need more information. Let's practice. Whoa, asbestos. Nasty stuff. Nasty, nasty stuff. So let's see if we can figure out the empirical formula for asbestos using the percent composition by mass given right over there. Okay? Pause and give it a shot. All right, welcome back. Let's see if you did the problem and got the same way I did. Again, I'm assuming you have 100 grams of asbestos. Oh, nasty stuff, full hazmat suit and all. But then I can convert each of these percentages, like 28.03% of Mg, magnesium, directly into 28.03 grams of magnesium. And I can do that for all of the species that make up asbestos. And turn them all into grams. And now turn that gram ratio into a mole ratio. And once you have the mole ratio, throw it into a pseudo formula. Oh, that thing is ugly. So divide by the smallest number so that you get a whole number integer, at least for one of the atoms in the formula. And when you do that, you're getting closer. But notice even in this formula here, your Mg 1.5 Si 1 hydrogen 1, how can I have half an atom? So I can't. So this is still not a good empirical formula, and you are going to have to maybe multiply it up to still get to an integer. So multiplying this by 2 allows me to get to complete whole number integers right there for the empirical formula for asbestos. Pretty cool, huh? All right, if you wanted to get the molecular formula again, you would need the molar mass. So this might be the molecular formula if the molar mass for the entire molecule of asbestos matched the molar mass for this formula's molar mass. Or maybe it's twice as big and its molar mass is twice as big. So a little more Work has to be done to get to molecular formula tense from empirical formula camp. Not much though, just a little hop, skip, and a jump away. Here's another website or two up there, over there I mean, and down there for you to go play with empirical formula practice problems. Okay? I hope you enjoyed this video on Blue Square practice problems for stoichiometry. Keep practicing really on all those websites. Workshop number 1 in our first lab has more practice problems on it as well. And we'll have one more video for those black diamond stoichiometry problems coming up. Please check it out. If you want to see how Mount Moleville becomes nothing but black diamonds. Ah! All right. Good luck. Please feel free to ask any of the instructors, including myself, any questions you have about stoichiometry, and I'll see you soon. Bye.